Okay, we're back. This is, I believe, page 5 of the notes. Example 9. So now we're up in the game a little bit. We're talking about a situation where we are rolling 2 dice. Okay, so if I roll 2 dice, I want to find the sum, right? I'm going to roll 2 dice, add them up. I want to list the sample space. What are the outcomes that can occur? So if I throw 2 dice down and add up their values, they could add to 2 or 3, 4, 5, 6, 7, 8, 9, 10, 11, or they could add up to a 12. Okay. Well, the question they're asking is, what is the probability of rolling a 3 or 4? That's what I'm looking for, the probability of a 3 or a 4. Okay. Some people would incorrectly say, well, okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 possible things, and there's 2 ways to get a 3 or a 4. That's not correct. Because what we're missing out by just looking at the sample space is we're not recognizing that there's more than one way to get a 3 and there's more than one way to get a 4. So we're not truly counting the correct number of ways to pull off a success. Same, we're not totally counting the correct number of ways that we can get any of these numbers, right? There's more outcomes than just 11. So what we've done is we've kind of developed a table here. Here's the results of throwing 1 die, the results of throwing another die, and I'm going to add them up. So if you get a 1 and a 1, they sum to 2. If you first roll a 2 and then a 1, they add up to 3. If you roll a 3 and a 1, they add up to 4. And so on. And let's just kind of keep this going. If you roll a 1 and roll a 2, you get a 3. Roll a 2 and a 2, you get a 4. And you can probably quickly see a pattern pop out of here. And once you do, oops, that's crazy 5. Feel free to use it. Six, 7, 8, 9, 10, 11, and 7, 8, 9, 10, 11, and 12. And all in all, there's 6 by 6. There's 36 possible outcomes here. So the number of outcomes that can occur when I roll 2 dice, there's 36 different combinations that can occur. Okay, these are all of them. Now to get a 3 or 4, there's 5 opportunities for that to happen. I can get a 2 and a 1, or a 2 and a 2, or a 1 and a 2, or a 1 and a 3, or a 3 and a 1. So there's 5 different ways that can occur. So the probability of getting a 3 or a 4 should be 5 out of 36. Okay. A definition we got to talk about now is this idea of disjoint sets. Events A and B are said to be disjoint or mutually exclusive if they cannot occur at the same time. In other words, when you look at their Venn diagram, there would be no overlap between the two things. Okay. So again, some books use the word disjoint, others use mutually exclusive. I kind of go back and forth between the both. It simply means that the events cannot happen at the same time. So, for example, if one event is that it's raining, the complement would be that it's not raining. Those can never happen at the same time. And in fact, we'll see down below, an event and a complement can never occur at the same time. They are mutually exclusive. So here they give us some examples of mutually exclusive events. Randomly selecting someone that's a Democrat or randomly selecting someone that's registered Republican. They can't be registered for both. It's one or the other. If you were to flip a coin and the event that it lands on heads versus the event that it lands on tails, they cannot occur at the same time. They are disjoint or mutually exclusive. Things that are not disjoint that may occur at the same time would be randomly selecting a student from a stats course and randomly selecting a student from a business course. You could have students that take stats and business at the same time, so there could be overlap. In other words, if I said, where are my stats students at? Where are my business students at? There could be some overlap there for people to say, well, I'm in both. Disjoint sets, there will be no overlap. Okay. So kind of alluded to this already, that the complements of events are always disjoint. Like if it's what did I say? If it's raining out, the probability that it's raining outside and the probability that it's not raining outside, they are complements, right? Or they're complementary events, I should say, raining and not raining. They cannot happen at the same time. They're disjoint. And because if you have two disjoint events, we know that there's no overlap in the Venn diagram. That means that the intersection of those guys would always be 0. Again, remember, intersection is saying where's the overlap? Well, they have no overlap, okay? Okay. I'm not going to ask for, the definition of disjoint or identify if things are disjoint, but where we need this is later we're going to get some advanced probability rules that are going to help us do probability easier. And depending on whether or not the events are disjoint or mutually exclusive is going to sort of determine how we handle those rules. Okay, so we've got two rules here. Let me take that back. Right now we are going to focus on the addition rule, okay? We are later going to learn the multiplication rule, but for now we're learning the addition rule. And the addition rule is a rule that is synonymous with an OR statement. So when you have an OR statement, you will probably be using the addition rule, okay? All right. It makes a lot of sense, but I think that when you look at just the formulas on the face value, they could be a little intimidating. So let's just think about it. Let's think about it with a Venn diagram. So let's say that I've got two events. There's event A and event B, and I'm going to draw them with some overlap. So they are not disjoint. If I'm looking for the probability of landing in event A or event B, well, it really is as simple as just add up the probability that you'll land here in event A, add to that the probability that you'll land here in event B, but then look what happens. If I take everybody that's in bubble A and I find the probability of being there, and everyone that's in bubble B and I find the probability of being there, the stuff in the middle got double counted. Right? And so when I, calculate this probability and this probability, I've counted that space twice. That is the reason that we then subtract the probability of landing in the intersection. It's to remove that double counting. Now, if you've got two events here that are disjoint, so I've got A and I've got B, and there's no overlap, then to find the probability of the union, well, let's just find the probability of event A, of landing in that bubble, plus the probability of event B, landing in that bubble. There was no double counting, and therefore there's no need to subtract any sort of intersection here. There is no intersection. Okay? I always just stick with this formula, this idea, because if it happens to be that these are disjoint, then this is just 0, and it collapses into this formula right here. So let's take a look at this example here. It says here we've got, this is known as a two-way contingency table. It's sort of like an idea of a Venn diagram, but except in a table format. It's basically laying out our data and sort of categorizing it for us. So we've got pre-employment drug screening results of 1,000 employees. So they gave a drug test to 1,000 employees, and here's what they got. They had broke this down into people that use drugs, and of those people that use drugs, they had 44 test positive for drugs and 6 test negative for drugs. And then they had all the people that do not use drugs. 90 of those guys actually still tested positive for drugs, and 860 of them tested negative for drugs. Now, I'm sure you've heard of this stuff before: true positive, false negative, true negative. Notice what's going on. If you got a positive test result, then you're positive. If you got a negative test result, you're negative. The true or false just determines was it correct or not. So here, these guys used drugs and they tested positive for drugs. So it's a true positive. The test worked. Here, these guys do not use drugs, but they still tested positive for drugs. So that would be known as a false positive. Yes, they tested positive, but it was false. It was wrong. Okay. A false negative. So here I've got these guys that use drugs They tested negative for using drugs. Well, that was false. They do use drugs. It should have been positive. So it was a false negative test result. And then lastly, a true negative test result. These are the guys that do not use drugs. So they should have tested negative because it was true. It worked. The test did what it should. We call that a truly negative response. Okay. So the question is, if one subject is randomly selected from the 1,000 subjects given a drug test, find the probability of selecting a subject who had a positive test result or used drugs. I want the probability of positive result or used drugs. I highly recommend you write down this rule every time you'd use it, because it's going to do two things for you. One, you're going to memorize the rule. Two, you're sort of writing yourself a list to follow. So the way I would do this, again, I'm trying to figure out what's the probability of landing in this bubble or in this bubble. Okay. So the first thing I would do is find the probability of getting someone that tested positive. Positive test result for drugs. That's like being in the yellow bubble up there. And then I also want to add to that the probability that someone lands in the blue bubble, that someone uses drugs. Let's just do it this way. Now, do I have anybody that I got that counted twice? Let me shed a little light on it here. I'm looking for the probability that someone gets a positive test result. So I say, okay, if you got a positive test result, raise your hand. And all of these folks raise their hand. Those are all the people that had a positive test result, whether or not they use drugs. Or I want the probability that someone just uses drugs. So I said, okay, if you use drugs, please raise your hand. And all these people raise their hand because they're the ones that use drugs. So do you notice that this group of folks got counted twice? I counted them when I said, did you get a positive test result? And I counted them when I said, do you use drugs? So because there is overlap, if I find these individual probabilities, I'm counting those guys twice in that calculation. I need to then remove the probability of someone getting a positive result and using drugs. I need to remove that overlap. Again, so I'm using this rule right here. Well, there were 1,000 people tested. And of those 1,000 people, how many of them had a positive test result? 44 plus 90, that's 134 people had a positive test result. Plus, out of 1,000 people, how many use drugs? The success would be how many ways can we pick someone that uses drugs? Well, there's 44 and 6, so there's a total of 50 people that use drugs. But again, that 44 was double counted. So now I need to then remove that double counting. I have to subtract the probability that I would pick someone that uses, that tested positive and used drugs. Well, that would be 44 out of 1,000. Okay. And if I'm doing my math right, that comes out to 140 out of 1,000, or 0.14, or 14% chance to pick someone that tested positive or uses drugs. That was as far as I was able to get on this video, so I'll start another one. Bye.